In the previous lesson, we talked about deep Q-learning, which focused on estimating the value of state action pairs. This lesson will look at the other school of reinforcement learning, estimating the policy directly. Thankfully, most of the engineering and operations work remains the same between deep learning and policy gradients. That means we'll be able to focus on just the algorithms. Let's start with policy gradients, which is the basis for actor-critic. For deep Q networks, we built a network that takes in state properties and predicts the value of each action. On the other hand, policy gradient-based algorithms take in state properties and returns the probability we should take an action given the state we're in. This can be extremely useful for a couple of reasons. Consider a game like rock, paper, scissors. A deep Q network would assess the value of each hand and select the action corresponding to the maximum value. Whenever it feels it's in the same state, it'll always choose the same action, making it easy to exploit if the opponent catches on. On the other hand, if we find the probability to take an action, even if we're off by a little bit, we can still surprise our opponent. What was strange to me when I was first learning policy gradients is what we're fitting against, which is our chosen action given the state. I thought to myself, wait a second, I thought that was what we were trying to find. How does that work? The secret sauce is in the loss function. Since our goal is to find the optimal policy, we can assume that the probability of taking the optimal actions, or A star, in state S should be 1. The fancy gradient with pi, that's the change in our policy that moves towards the optimal action. There's a couple gotchas to this, which are pretty similar to the gotchas to policy iteration. Since we're following the policy we're training on, we might pick an action that's locally optimal, and then keep picking that action because the local optimum increases the chance to do that action. To counteract this, we'll divide our weight updates by the probability we have to choose them. That way, actions with high probability don't overpower low probability actions. Those with a good eye for calculus might recognize this as an opportunity to do the chain rule. The derivative of the natural log of x is 1 divided by x, so we can simplify this expression into a log function. The other gotcha is based on our training sets. How do we know which action pushes towards optimal rewards? For that, we'll give our neural net another parameter, g of t, which represents the value we saw from completing that action during training. When we put this action with code, this is what our custom loss is going to look like. We're going to force our predicted values to be between two really small numbers. The closer the input of our logarithm gets to 1, the closer the logarithm fattens out to 0, which means it will stop training. We multiply the result by yTrue, or the one-hot representation of the action we chose. That means we're only training on that action. Finally, we multiply it by g to add in our observed rewards. There are a lot of different ways to play with this, and I'd like to give a shout out to an author who helped me understand this much better. If you'd like to see a larger breakdown of the math here, I'd recommend checking out the article and link below by Chris Yoon. This would be the code for the full neural network. What's interesting here is that we actually have two models which share neurons. One is the policy, which takes in state and the value, g, to train. The other is the predict network. We don't have the current state value when we're choosing an action, so that's why we have a separate model with separate inputs. So what is this g, and where does it come from anyway? It's actually our good old friend, TD Lambda. We'll alter our memory buffer so that it takes one full episode and clears when we sample it for training. When we get to fitting our data, we can finally calculate g, which I've labeled as discount MB. Any chance this math here looks familiar? I hope it does because it's TD1. We're only calculating TD1 across the episode, so we don't need to worry about the value of the states. We'll just apply gamma to our rewards, working backwards to the episode so we can keep track of S prime's future rewards. One thing that's different here over TD1 is at the end, we subtract from the episode's average and divide its standard deviation. This is just one more trick to help prevent the policy gradient from going towards the local minimum as episodes become more comparable to each other. Finally, we need to teach our agent how to act. The new act function is beautifully simple. We feed it our current state observation, and in turn, get probabilities for each action. Then, we can use NumPy to randomly choose from them. That's all there is to it. We can take the code that we have here and swap it out with what we have for our DQN, and our agent will go to town. There's one last algorithm I'd like to share with you, and it's pretty awesome because it will bring together everything that we've learned. We'll look at it in the next video.